Thank you very much. It is fantastic to be here. So good morning, Melbourne, and good morning, YOW. Thanks for walking all the way down the hallway to join us. Some of you, this is the first time you came down here. You didn't even know there was a conference down here. But welcome. I'm thrilled to be back here. This is my second tour with YOW, and it's been a fantastic 2 weeks here in Australia, and it's really exciting, actually, to be finishing up the tour in probably the greatest city in Australia, right? Melbourne, certainly. So I'm glad to be here. Thank you all for having me. We got a lot to get through today. I will probably not have much time for questions, but I'll be around all the rest of the day if you have any thoughts and questions. But I'd also love for your feedback. That's my Twitter handle. Getify is how I'm known on GitHub and Twitter and all the other places online that matter. So throughout the talk and afterwards, any feedback, questions, thoughts you have, please share those with me. Let's make sure that we are all on the same page about what this talk is, because there's been some confusion in the previous cities about the title, that this is a productivity talk. It is not a productivity talk, so I want to get that out of the way. Let's make sure, actually, well, I don't know how to cancel. Why is that taking so long? Let's see. I guess we just have to, okay. Let's make sure that we're all on the same page about what this talk is. How many of you in the room would say you're not primarily a JavaScript developer, that you do something other than JavaScript development? Most of the room, fantastic. That's what I planned on, that's what I expected. As you know, I'm a JavaScript developer, and all of the code today will be in JavaScript, but this is not a JavaScript talk. This is a talk about a concept that I believe to be cross-cutting on all of the tech stacks that we work in and all of the systems that we build, and in fact, cross-cutting from both front-end and into back-end. So I want to talk about the cancellation of asynchronous operations. That's the talk. And I'm going to use JavaScript as a means of illustration, but not as a means to poke fun at or say that JavaScript is somehow uniquely either better qualified or less qualified to do so. These are problems that we can see across all the tech stacks. And in fact, as I was researching for the talk, I was hoping to find other people talking about other things, and all I found in my Google search results were me talking about it. So this is a problem that is universal that we're not talking enough about. So a quick bit about myself before I jump in. As I said, I'm very much into JavaScript. I teach and speak about JavaScript for a living. I've also written about JavaScript, so I've written a number of books. The You Don't Know JS book series is probably the one I'm most well known for. You can read those for free online, also purchase them if you like them. And then my latest book has been out about a year, Functional Like JavaScript, a pragmatic way of doing functional programming in JavaScript. Same thing, you can read it or purchase it. This is awkward. How do I get rid of this? I got to cancel this. It won't cancel. Let's see, I guess that's the right button. Okay. Man, hope that doesn't happen anymore. All right, so let's jump in. We all know this to be true, right? It happens. In fact, there's a running theme throughout this conference that failure is something that we should be planning on, that failure happens. And we shouldn't be surprised by that. We should be planning for it, and we should be taking care of it directly. And I'm going to extend that to say that even though that is definitely true, one other thing is absolutely certain about our code, and yet we don't plan for it, and that is that cancellation happens. We tend to think of cancellation as something that may or may not occur, that we hope doesn't happen, that it's an exceptional path. But I'm going to tell you today that cancellation is an absolute guarantee. It is absolutely certain that cancellation will happen, but I want you to keep that idea of certainty in your head, because that's going to be a running theme throughout today. All right, so cancel. We certainly understand an idea of cancel. It means to sort of stop something. So some synonyms of cancellation: abandoning and killing off and terminating. These all feel like very final sorts of things in our application, meaning our application stops in some meaningful way as a result of cancellation. And those are all true, but I think there's more to cancellation even than that. So what about pausing? Is pausing a form of cancellation? And I will argue today that it is. Indeed, and it's much more complex than simply halting a program. The question of how do you pause something and then potentially resume or potentially stop it altogether. What about undo? What about the idea of stopping where you were and not just simply finishing at that point, but having to backtrack? Is that a form of cancellation? Is that a complexity in the cancellation space? And these are all things that I think encompass the idea of cancellation, but we're not talking about and planning for these very specifically. So let's categorize them. On the left here, we would say these are very final things. We would think of them as events. These are events that occur and they're very final, meaning there really isn't anything meaningful in that particular code path to occur after these things have happened. But on the right-hand side, these, the more complicated ones, recovering from something, even rolling back a set of states in your system, if those are cancellation, then they speak to the idea that maybe we should be modeling, and not maybe, actually certainly, we should be modeling these not as events, but rather as states in our application. So that's the first point I want to make to you, is that we are at the wrong level of abstraction when we think about cancellation merely as an unexpected event. Events are unexpected, but states are expected. They are planned for. They are carefully planned out and they are carefully considered. Cancellation should never be an unexpected exception. It is not as if we could not have possibly imagined that something would occur that would cause the system to stop or to go into one of these states. And yet we often treat it as this, wow, I didn't expect for that to occur. It should absolutely be a predictable state. So if it is a state, then what is the enemy of our state in our systems? What is the enemy of our state? Well, I'm going to argue to you today that the enemy of our state is uncertainty. That if we do not plan for something, it will still occur, and that puts our system into this unpredictable, uncertain sort of condition. How many of you have heard of the halting problem before? This is one of the classic problems in computer science, and the halting problem asks, given any particular program, could I prove that that program would run forever? In other words, here's a representation of a program in a state diagram. Do I know that it's going to spin forever, or do I know for sure that it will stop? That's fundamentally the question being asked. And we all know that to be a very important sort of a question, because if you knew for sure that a program was going to run forever, then you absolutely would want to step in at some point and stop it. You would want to cancel it, right? But how do we know whether it would run forever? So this is a very critical question that computer scientists from the very beginning tackled. And it turns out mathematically they were able to prove that it is impossible to solve the halting problem. That this is an impossible problem. You cannot prove that a program will run forever. So we shouldn't waste any more time thinking about how do I prove that my program is going to run forever. We have to deal with cancellation in that sort of uncertainty. I'm not sure if it will run forever or not. And the way we deal with that sort of uncertainty where we can't absolutely prove a particular solution, so we do what any good computer scientist does, we approximate. We approximate with timeouts. Timeouts are how we basically say, listen, if it's taken, for example, 5 seconds for some operation to occur, then I'm going to assume that that is indistinguishable from it taking infinity, an infinite amount of time to occur. So if it's taken 5 seconds, I'm going to say we've crossed my threshold, I'm going to time out, I'm going to cancel whatever that operation was. That is our approximation for the solution to the halting problem. How many of you have heard of Schrodinger's cat before? This is a famous thought experiment by the physicist, the quantum physicist, Schrodinger. And what's interesting, it's very morbid, but what's interesting about this experiment, it was applied for quantum mechanics, but it was designed to make a statement about the real world. A statement of paradox, a statement of absurdity. See, in Schrodinger's experiment, what he did was he said, what if we were to put a cat inside of a box with a vial of poison, and a mechanism that could destroy that vial and therefore release the poison and kill the cat, but that mechanism would be controlled essentially through randomness. His thought experiment was we would use the radioactive decay of particles to decide whether or not the mechanism were to trigger and kill the cat. And then Schrodinger said this, what if we closed up the box and then we just waited a certain amount of time and we then checked to see whether the cat was still alive or not? Yep, he's still alive. Hopefully, as we keep checking, he's still going to be alive. No cats should be harmed in the making of this talk. So, he was making a statement that says, in this place where we can't actually determine the state of the system, from a quantum level, this is a mathematical proof that at a quantum level, that particle is actually in all of its possible states, and that's called quantum superposition. That it's actually all of those things at the same time. And we can say that in math and be like, okay, I sound smart, but when you talk about it in the real world, it sounds ridiculous to suggest that the cat is both alive and dead at the exact same time. And that was the point of the experiment, is to suggest that this uncertainty is absurd. It might come from the math, but it is absurd. we know that no two cats can occupy the box at the same time, right? There's only one cat in the box. Actually, you can do Schrodinger's asynchrony in JavaScript, in any sort of programming, but here I'll use JavaScript. Here I've set up a promise, and it's mimicking this idea of Schrodinger's asynchrony, of this quantum superposition in JavaScript. We're basically saying this promise will resolve potentially at some point, but notice that I'm using a bunch of randomness. We're using randomness here both to determine the timing and to make the decision about whether to kill the cat or not. So it is possible, although unlikely, but it is possible that this could run basically forever and never actually kill the cat, because it's all entirely based off of random, at least the best approximation of it that we can get on the computer. And so the only way for us to know if the cat has died is to open up the box and observe it. This is the uncertainty of the systems. And what I'm trying to get at is that the uncertainty of systems creates chaos within our programs. We should be avoiding that at all costs. So I got to thinking, what about canceling a cancellation? What would that mean? What is canceling a cancellation? Well, actually, canceling a cancellation is an awful lot like a pause, isn't it? We thought we were going to stop something, and then we decided, no, I want to keep doing it. You get one of those dialogues where you've tried to click to delete something, and it pops up and it says, are you sure you want to do this? And you say, no, actually, I don't want to do that. And you cancel the cancellation. In programming, we may model this. Here's a timeout. It's a promise that's going to reject after a certain amount of time, but I do something interesting, which is I add a cancel method to the promise that allows me to clear that timeout. Importantly, the cancel method here does not put the promise into a determinate state, at least from our ability to observe it. It simply says this promise will never resolve. It clears the only thing in the system that would have possibly resolved this promise, which means from on the outside, and in terms of our observation, this is in an uncertain, indeterminable state. And some of you have heard of cancelable promises. That is essentially what cancelable promises are. Because this looks okay, but I'm telling you it's the wrong level of abstraction. It is the wrong level of abstraction for us to model the idea of cancellation at this individual operation level like that. Because while this looks okay, we just pass in that too long promise, and we know that if it's taken too long, it'll reject, and then the operation will be abandoned. But actually, we don't know, and the reason we don't know is because there's that cancel method floating around somewhere. And as we've passed this promise around through our entire application, and indeed beyond the borders of our application, any part of our system could decide to call that method. Say they don't care about the promise anymore, so they call cancel on it, and now this part of the system is in an indeterminate, uncertain state. Because we don't know that it has been canceled. The only way for us to know that it's been canceled is to wait to the death of the universe. This sort of uncertainty is where the problems are coming from in our applications. So I would just say to you, if you've been following along and if you were sad that we didn't get cancelable promises, I'm glad that those died because they enshrine in our system one of the bad anti-patterns, action at a distance. I do something over here, and something that seems entirely unrelated is affected. This is bad design. It leads to difficult to understand and maintain systems. It puts our systems into an unpredictable state, and I would say you should just say no. Okay, so let's talk about this idea of randomness, and I'm going to sort of equate this with complexity. And I want you to understand why I'm equating it with complexity. How many of you have heard of Arthur C. Clarke, the famous science fiction author? And Clarke's 3 laws, the most famous of which is Clarke's 3rd law. And Clarke's 3rd law says this. It says any sufficiently complex system is indistinguishable from what? From magic, right? So if it's very, very complex, then we basically look at it and say, well, that might as well just have been magic. I'm going to tweak this phrase just a moment. I'm going to tweak this just a tad and say any sufficiently random system is indistinguishable from magic. Any sufficiently complex system is indistinguishable from randomness. Okay? I'm equating these two because as complexity goes up to infinity, so does our observation of that system as if that system were driven by randomness. You cannot simply cancel. It's not possible. Let me make it very clear that the choice to have cancellation, and it's not really a choice, you must have cancellation, but the choice to have cancellation introduces complexity. It is not the case that I'm saying you cannot have complexity, but you should not have unpredicted and unplanned for complexity. You must plan for these things, and that is the point. Don't follow down the path to the mountain of uncertainty. All right. So what kinds of things are we talking about canceling? Let's first start by talking about the user, because absolutely, I guarantee you, users want cancellation. Let's talk very briefly about a few of the things that users are expecting. The stop button in the browser. How many of you have ever been waiting for a really long loading page, and you've been thankful to be able to just click stop and say, I give up, cancel that, stop trying to load that. It's obviously never going to load. How many of you have ever got a prompt in the browser like this one from IE that says, stop running the script, and you're like, I don't know what to click here. Should I click yes or no? What's going to happen? We're in this uncertainty state as a user, and that's not a good place to be, is it? Or what about this one? How many of you have gotten the prompt before that says, would you like us to throw a bunch of notifications at you from here to the end of time? No, block, please. At least they make that button very clear. Cancel that right away. Spinners are a favorite, and they're getting more and more so. In the React architecture, as a matter of fact, they're basically saying, listen, we'll throw up a page, and all these little bits and pieces of the page, if they're not ready to be displayed yet, we'll put a placeholder there, which is essentially a spinner. So our future is to just have spinners all over the place. I'm super excited about that. I hope you are too. This is my favorite and most hated. Whatever it was that I was doing on my system, when the beach ball hell pops up, I'm immediately thinking, oh my God, please stop. Whatever that was, it's not important. Please stop. And yet I have no way of actually telling the system to cancel, do I? And that's where our frustrations come from, because users expect to be able to cancel subscriptions. Or is this the cancellation of the cancellation to bring the subscription back? I can't figure it out. What about uploading files? These things take too long, especially if we're on terrible hotel Wi-Fi. Please cancel this. And my favorite of all, when you're checking your email, if it goes too quick, you're like, oh, it certainly didn't even check, right? But if it goes too long, I know, we're so paranoid, like keep doing it like 15 times because we're not really sure that it checked. Certainly there's at least one email there. But what if it goes too long? If it's like a minute or two, I'm like, listen, I don't care about my email that much. Close the program and cancel it. The point is, users care about cancellation. And if you're a product manager, you know this has to be a first-class citizen. Unfortunately, it's all too often a second thought that we bolt on at the end when somebody complains about one particular use case, and then you have to go re-architect the system so that that one little thing can be canceled. We should be building this as a first-class citizen in all of the design. Just like accessibility and offline ability and all those other things, cancelability is one of those other illities that we should be planning for. So now let's talk about developers, and oh my God, this is a terrible video. Let me cancel that quickly. What do developers care about with cancellation? Well, the ones that are obvious, we know that they care about canceling timers. So we can do something like an interval, and then later we could call clear interval to tell this stop spinning once per second forever. Developers love to cancel AJAX calls. That's an important one. We want to be able to cancel AJAX calls. Now, this is interesting because we shipped the fetch a couple of years back without any mechanism for cancellation, and developers went nuts. They tore into all of the mailing lists and the standards bodies and things and said, how could you give us no cancellation of an AJAX request? Even though none of you had ever done any cancellation of an AJAX call before, as soon as we shipped an API that's not capable of it, now we get upset. Don't take away my cancelable AJAX. This is important, right? And even events. Events are pretty obvious. We would like to be able to listen for an event and then do something like remove event listener to say, listen, I don't care about that event anymore. I want to cancel the listening of a particular event. So those are the obvious ones, the usual suspects. But it leaves me asking this question, what about all of the other things? Everything else. Because all of the other things are things that occur, and especially if they're asynchronous, they're all things that we should be considering about cancellation. How about the file system? How often do we, in our own hubris, say, well, listen, if I try to load a file from the file system, it'll certainly be right there present for me to get. It'll only take a couple of milliseconds, I'm sure. No problem. I don't even need to design the core API of Node to have any mechanism for cancellation. Just fire it, and it doesn't matter how long it takes. until you fire it against a file that's on a network drive, and it takes 15 hours. Wouldn't you have liked to have been able to have a sanity check to step in and cancel that? As a matter of fact, stream-based operations are all over I/O systems like Node, so we see stream operations, and there is a sort of fail-safe in cancellation of streams, which is to just literally kill the stream entirely, destroy the object. That's not very graceful, but it's the sort of brute force way of saying, listen, whatever this stream is doing, stop it, cancel it, terminate it. But that's not enough. That's far too low level. It's at the wrong level of abstraction. In fact, we have lots of stream-based operations, socket-based operations. If you're connecting between two systems or between a system and a user's system, you absolutely should have some sort of way to step in and say, listen, cancel that. It's taking too long. It's taking up too many of our resources, or it's taking too long. Databases are another of my favorites. With so much optimism, I guess, just say, listen, if I select a group of records from the database, it'll come back right away. Couldn't possibly be that this select might take minutes or hours to come back because the database was in some other read-locked state or the system was down or something. Look, just make the request. It doesn't matter how long it takes. The records will come back when they come back. There's a theme that I'm trying to get out here, and it's true with child processes as well, which is that there is nothing in your system that is asynchronous that should not have cancellation built into it. There is not a single operation that you can tell me about where I'm like, I guess it doesn't matter. Let it take as long as it needs to. Cancellation must be a first-class citizen, and yet we're not thinking about any of these things. Again, we have a really low-level system with child processes, my favorite. To get rid of a child process, we send the SIGINT or the SIGTERM operating system level signal to it. That's our way of telling it, stop doing what you're doing. These are poorly designed systems because we're just expecting that cancellation will be an exceptional event. And we should be planning at the right level of abstraction for it to be a guaranteed state of our systems. And I know you're saying, this is boring. Why is he talking to me? It's like my mom trying to get me to eat vegetables. I don't want to talk about this stuff. This is not exciting. Why is he so riled up? Why is there so much emotion and ranting up on stage? I get it. I get that it is one of those things that it's like eating your vegetables. You know you should do it, but nobody wants to do it. Nobody wants to spend time talking about it. That's why nobody is spending any time talking about it. But I'm trying to tell you that it's the path to the system complexity that so often frustrates us. Because this is absolutely the weakest part of our system design. We're pretty good at failure-proofing our systems, but we're not at all good at cancel-proofing our systems. So, for the rest of the talk, instead of all the funny memes, I am going to get into code, and I'm going to use JavaScript. There's no more funny memes after this one, all right? It's going to be all code from here on out, and I want to dig in to some of the use cases around cancellation, why cancellation works in certain ways, and really, at the end, try to cast forward a vision that we should be solving this together regardless of the tech stack. That we should be thinking about cancellation in a much more holistic sense. So let's dive into some code. My favorite of the use cases that sort of complexifies cancellation is when it's a conditional cancellation. You know, you have some operation on the page that might take a long time, so you have a spinner for it when the user clicks for some new results and you throw up a little spinner, for example. And then the product manager comes back and says, it's really ugly when that spinner flashes up for a split second every single time I click the button. Can you only make it show the spinner when it's going to take a really long time? And you're like, silly product manager. How am I supposed to know that it's going to take a long time before it's taken a long time? So we've invented debouncing. Essentially debounce this cancellation, so only show the spinner if the operation that I want to be able to be cancelable has taken at least 500 milliseconds, then show the spinner. So I just set up a simple little timer, and this is pretty easy to use in my application. I just, at the beginning of a set of operations, queue up the spinner, and then when I'm done, I call hide spinner. And it abstracts properly inside of itself that whole timing thing. It cancels the cancellation, if you will. A quick note on observables. For those of you that are in the JavaScript space or have done much reading in the JavaScript space, when you do any kind of research about this, you will inevitably find people from the observables, the reactive programming crowd, that will tell you, listen, observables have already solved this problem. You can simply unsubscribe from an observable, and that magically fixes the whole cancellation, and that's why they tell you, build your entire app out of observables, problem solved. It's not quite that simple, because there's a notion of both hot observables and cold observables. With a hot observable, unsubscribing is basically just stopping listening. It doesn't do anything to actually cancel the system. And with a cold observable, like I've shown here, it does actually send a signal back to the source to say they've stopped listening, but this is an implicit system for cancellation, at best. And that's not good enough. We need to raise the bar in terms of our design. So as great as observables are, and as much as I like observables, I'm here to tell you that observables are not enough. We need to be thinking at a higher level of observation. Starvation. This is not about how hungry I am and when's it going to be lunch. This is about system resources, okay? System resources. So this is a big problem whenever you have a concurrent system. Concurrent is a fancy way of saying either parallel or asynchronous. When you have a concurrent system, many, many things that are happening. If one of those things, either accidentally or intentionally, starts spinning really fast on system resources like the processor, it has the effect of starving out the rest of the concurrent processes from being able to do anything. You can probably imagine from that basic description that this is a huge problem that we want to avoid. And there's lots of research into the topic of starvation. And because there's lots of research, you would think that new systems, those that have come up within, say, the last couple of years, you would think that those systems would definitely not make themselves susceptible to starvation, right? Because this has been known about for decades, that starvation is a big problem that we should avoid. Well, I have news for you. We shipped promises in JavaScript, and then we put the async await function around them, and we said, no big deal, starvation's not that big of a problem. I brought this up on the spec list that it is far too easy to create a starvation scenario with the microtask queue of promises, because that timeout, that timer down there, that's never going to run. Even though it's got 0 on it, it's never going to run. And the reason is because the microtask queue is going to run aggressively and never let any of the rest of the system, it's never going to yield back to any of the rest of the system. This is terrible design. I love promises, but this is completely ignorant design to say, well, we don't care about starvation. And when I brought it up on the specification list and I showed them actual code that leads you into a starvation scenario, you know what they said back to me? Well, you're the first person to complain about it, so it must not be a problem. I'm not lying. This is ignorant. We need to be thinking about and planning for these things. This is a great blog post, by the way, and a couple of my next points came from or were solidified or more concrete because of this blog post. And it's not even about JavaScript. I was thrilled to find a blog post that was actually about a different language. This is about Python, but it's about cancellation. It's a fantastic blog post, so go and read more for details on this particular topic. And in this article, it makes this fantastic point about the difference. It was an idea that I had, but I couldn't put words to it, and now I can articulate for you the reason why I say it's at the wrong level of abstraction to think about cancellation as an event. Because in circuit design, we have this idea of edge-triggered versus level-triggered. Edge-triggered meaning whenever the circuit goes from 0 to 1 or from 1 back to 0, we observe that that has occurred, and then we do something with the system. That's edge-triggered. But level-triggered is to simply say, whatever level that we are currently at, are we at 1 or are we currently at 0? That's the state of the system that we know that we're in. So in other words, edge-triggered versus level-triggered is essentially event versus state. And the point that's made here is that events can be missed. So if I said this is a very crude way of illustrating it, it's the difference between listening for a cancel event and looking at a cancellation state. Events can be missed, but state is not. State is always present within our applications, and if we are intentionally modeling it, we can transition correctly. And event composition can be quite complex, but state transitions are often very straightforward, at least if you're intentionally doing it. Another point that this article makes, which enforces the point that we're dealing with the wrong layers of abstraction when we talk about cancellation. It's this idea of timeouts versus deadlines. This operation here I'm going to fire off to ask for some tweets from this weird guy named Getify. And I want to know whatever the newest tweets from Getify are. So this looks like a pretty reasonable system, and you notice over here that I've got a timeout of 3 seconds. I've said, listen, wait at most 3 seconds to get any new tweets that he may have, because I care, but not that much, just a little bit. Okay? It seems reasonable to use a timeout like that. If we've got a fetch new tweets API that knows about timeouts, just simply pass in a number like 3,000, and everything should be fine, right? Well, not quite so much, because if you look at the implementation of that function, you'll notice that it actually calls several other functions. It calls the fetch user, and then it calls the fetch timeline. And you'll notice, importantly, that it takes that 3,000 and it simply passes it along to all of its constituent children. So now instead of us thinking that the high-level operation is going to take 3 seconds, this one actually might take 6 seconds, right? But actually it's much worse than that. We actually can't predict how long this system will take because we have no idea who they call and who they call and who they call. And if they're passing that wrong abstraction around, it actually could be indistinguishable from infinity. So we thought we were building a good system, but we built it at the wrong layer of abstraction. Instead, we should build a deadline, like a timestamp in the future that everybody can agree on. I have to finish by that point. It doesn't matter how long any other parts take. We have to be completely done by this point. So I set up a simple little function called deadline here to calculate an absolute timestamp 3 seconds in the future. And I pass that deadline along. And now my fetch new tweets, when it passes that deadline along, this one signal, if you will, this one state that we can observe that we get into is that the timer has passed that particular timestamp. So we don't have any sort of leveling problem here. We don't have any leveling of abstraction problem here. Quick note on serial versus concurrent cancellation. Serial is just a fancy way of saying doing one thing and then the next thing and then the next thing. In other words, B has to wait for A. And concurrent is a bunch of things are going to happen in parallel, right? They're going to happen about the same time over the same period of time. So if we're doing serial, we're going to use JavaScript's fancy new async await syntax that everybody's so much in love with. And the characteristic nature of serial asynchrony is when you see all of these awaits, one right after the other. Meaning that step 2 is waiting for step 1 and step 3 is waiting for step 2. Sometimes that's exactly what you want. If step 2 is dependent on step 1, then you absolutely need to make it serial. But what you'll notice here is that to make this cancelable, I've had to do a race abstraction at each one of those steps. I've had to set up a too long timeout, which, by the way, even though this is now a promise instead of a deadline, it is actually at the right level of abstraction here because that promise will expire after 3 seconds no matter how many times it's passed around. No matter what level, it's entirely absolute to that, essentially to that timestamp. It will transition into a predictable state after 3 seconds, and that state is something that I can observe no matter what level of abstraction that I'm at. So I have this too long promise that I'm listening to, and I tell all of those tasks, hey, you have this much time. I set up a promise.race. You have this much time to finish, and if you don't finish within that time, we're going to give up and move on. So it seems reasonable, right? Except, so I forgot about concurrency. So concurrency is the same kind of idea. We're going to set up a race, but rather than setting up a race with each of the tasks, we're going to pass promise.all as the operation. So promise.all is going to listen for all of these promises in parallel concurrently. And if all of them finish within the allotted time, great. But if any one of them has made it take too long, then we give up on the whole thing, the whole shebang, and we cancel out. So this all seems pretty reasonable, except what you missed is that my little utility here is fatally flawed. What you missed is that my utility is fatally flawed because it's only stopping listening to the operation. It's not actually canceling the operation. Stopping listening to it is not the same thing as cancellation. That thing is still going to keep running forever and ever and potentially taking up system resources, starving out the system. This is what I would call shallow cancellation at best, because we're not passing along that signal to any of the further children so that they know, hey, we've been canceled and we can stop. So to build a deeper form of cancellation, I need to actually pass that promise that represents the cancellation state, not the event, but the state. I need to pass that state along so that the rest of the system can see it. That requires, of course, that every step along the way, no matter how deep you go, that they're all cancellation aware, and that's my whole point. We have to design the entire system holistically to think about cancellation. At any point, if we get a weak link in the system that doesn't know about cancellation, all bets are off. It's not actually cancellation. I want you to imagine a kind of race in the Olympics where it's not just that everybody's trying to race and get first, second, third place or whatever, get a bronze medal, but what if we had a race where the first winner across the line wins, they get the gold medal, and then immediately after they cross the line, referees run out and start chasing and tackling all the other runners and don't even let them cross the finish line? I'd call this an XOR race. That would be a really fun Olympic event to watch. An XOR race, either A or B, but absolutely, definitely not both A and B. Okay? What this happens in our systems, we sometimes will ask to load a thing from 2 different CDNs, for example, and I don't care which one it comes from, but I definitely don't want 2 copies of it. I don't want to waste all the system resources and memory and network bandwidth and all that. So as soon as the first one finishes, make sure to stop the other one. Sort of create a binary pairing between the two. We can model this in programming. Here's one way of modeling it with promises, and I know this is real intricate, but I want to focus down on the bottom couple of lines 15 and 16. Here I have the two tasks. So task 1 is listening to promise 1. But task 1's promise, the thing that it's waiting on to see if it needs to stop or not, is actually canceled by the completion of task 2. So they are cross-linked. Task 2 cancels task 1, and task 1 cancels task 2. It works, but my God, this is ugly and awkward. That's because we don't have the systems that are designed to handle these sorts of actual scenarios. We wait until we run across a product manager telling us we have to do this, and then we try to retrofit our systems to handle it. And this is a terrible idea. Cancellation tokens are actually a much, much better way of at least stepping us towards a better solution. They are, in a sense, sort of talking about it at the proper level of abstraction, or at least in the right direction. Because a cancellation token is basically an external sort of state signal that anybody can agree that we can all listen to. It's similar to a promise, but it doesn't have all the sort of weird concurrency questions about promises and the awkwardness of API. A cancellation token wasn't even invented in JavaScript. It was invented in other great languages, and we just recently adopted it in JavaScript. It's a great idea, and we ought to just internationally standardize on cancellation tokens. It's the first building block that we can build proper abstractions around cancellation on. So here's how a cancellation token works. You construct this thing called an abort controller, and then you can listen to an event on its signal. Notice controller.signal on line 7. I'm listening for an event that tells me that somebody has said this cancellation token has transitioned into the state that has been canceled. That's the event side of things, but it is also a thing that has a state. I can look at a cancellation token signal and see if it is currently in the canceled state or not. So it's actually both. It serves both needs. If you really want to respond to things event-wise, instead of polling, it's got an event mechanism interface, but it also has a state interface on it. And the state interface actually turns out to be a whole lot better. So at some point, you call the .abort, like we do down on line 10, and it transitions that token into that predictable canceled state. The rest of the system then, if properly designed, can respond correctly to that new state. Okay? So cancellation tokens are not the silver bullet, but they're much more solid than anything that we've built up to this point, in my opinion. We need to be transitioning our way of thinking into cancellations as these predictable states. Good news, by the way. The fetch thing that we talked about before where it wasn't cancelable, they decided to make it cancelable, and guess what they chose? Cancellation tokens. So this is already becoming a standard. That's a big deal that it happened in the web platform standard, that they decided among all the possible ways to do cancellation tokens are the right way to do it. That's a huge deal, and we should follow their lead. We should start standardizing on that across all of our systems, not just JavaScript. All right, now async functions seem to be the solution to all of our asynchronous woes. But as I've been pointing out, asynchronous functions have these weaknesses because they weren't designed with these kinds of questions in mind. Actually, the questions were in mind. I brought up the point that async functions aren't cancelable years before they shipped, and they didn't listen to me. And then we shipped it, and they don't have cancellation. And surprise, it's a complexity in our systems now. It's an unfortunate, unnecessary complexity. You see, it's so nice to show a tutorial where you're like, hey, listen, I can just await on these different promises and everything's great. It always looks good on the happy path. If something didn't look good on the happy path, they'd never ship it. How many of you feel like you spend all of your time on the happy path? Not me. We didn't think about the problems that would happen if we have this black box that's just a fire and forget. We're putting all of our asynchrony inside of these black boxes. That is complexity, randomness, and uncertainty. So actually, to handle cancellation in these things, you end up having to put a promise.race at every single await statement. Ugh. Are you serious? I have to do that, and also I have to pass along the promise timeout, the timeout PR to all of the other levels. This is crazy, right? This is so intrusive to our design of our code. This is not what they showed on the README to convince me that I should switch to async functions. But this is what I need to have a system that's actually going to behave more predictably. Poorly designed system. That's why it's difficult to cancel. So I started trying to think about what would it look like if we could address some of these problems. And just as a quick little note, this little library that I wrote is not the solution, but I'm hoping that it's a step in the right direction. What I said was we need async functions, but they need to be cancelable. So I built a little library called CAF. And it's going to use another mechanism of JavaScript, not the async function, but the generator, to emulate the idea of an asynchronous function, but with a way for the external signal to come in and say, stop what you're doing right in your tracks. That's the first problem that we need to solve, is to not have these black boxes that are not externally cancelable. So here's how CAF works. You take a regular generator function, and you wrap it in CAF. A generator, by the way, is a one-to-one syntactic correspondence to an async function. It's just it uses yield instead of a wait, and it uses a star instead of the async word. But otherwise, under the covers, they're going to behave the same. The difference is that a generator can be stopped and an async function can't. So we're using these mimicked or these faked async functions to provide cancelability to our async workflows. You'll notice now that I don't need any promise.races at all these yield statements, because that's implied under the covers through the way CAF works. It's automatically going to do a promise.race against the cancellation token. I'm using cancellation tokens here. Why? Because we should be standardizing on cancellation tokens. Okay? So CAF is maybe a little bit of a step forward. It's a small little tool that I've been using now for about 6 months. Other people have picked up on it in production. We're moving, I hope, little by little in that direction. And by the way, because it uses cancellation tokens, you can interchange those tokens with cancelable fetch. But I'm not here to sell you on CAF, because there is still quite a lot of tediousness about it. It is still frustrating that I have to pass along the signal to all of those different levels. Because essentially, we're still solving the problem at the wrong layer of abstraction. We're still thinking about these as individual operations instead of thinking about a collection of states that need to be canceled. That's actually ultimately where we need to be solving this. So I'm going to leave you, in our closing moments, I'm going to talk to you about this idea of cancellation zones. And this is a super rough idea. This doesn't actually exist yet. But I'm trying to think forward. If we want to solve this at the right level of abstraction, what does that look like? Well, it looks like a whole set of states that are all aware of the idea that they could be cancelable and maybe even rollbackable. We collect all of these states together into what I call a cancellation zone. So here are these different operations. I've got like main and something and other, because I'm super creative with my naming for these slides. But these 3 different pieces of my system that all kind of talk to each other, I'm going to collect all of them together into a particular instance of a cancellation zone. Pass them all in and get back these wrapped versions of these things that are aware of cancellation semantics, similar to what CAF was doing. So now I can call, and by the way, I can set up the cancellation signal to either be time-based, a deadline or a timeout, or I could pass in a cancellation token, right? So either one of those sorts or both of those abstractions would be useful here. But I'm essentially going to say from the outside, this entire zone is either canceled or not, rather than trying to think about it at the wrong level in terms of step cancellation. And now when I call this function, it automatically propagates the signal along. Instead of me having to intrusively remember and forget to pass a signal and now something doesn't cancel right, it automatically makes sure to wire all these things up so that they all know that they're participating in this zone. And by the way, we could do all kinds of great stuff like having asynchronous call stacks and everything if we collect everything into a zone that knows about it. Even cancellation zones are not perfect, though. And by the way, this is not just about convenience, because you remember at the very beginning of my talk I mentioned the idea of undo. We haven't even talked about how you might solve undo. To solve undo, in other words, to be able to take some arbitrary state that you've arrived at and then say, I want to walk back my state several steps, you actually need a whole different way of modeling state based upon immutability. Talk about intrusiveness, right? Well, I think maybe cancellation zones lead us towards a way of modeling the entire state transition between all of those steps in those immutable ways so that a cancellation zone could trivially walk back the state of our system. So what's missing right now in terms of anything that we have is atomicity. It's easy in databases. You can have a transaction and just roll back the transaction, but it's really hard in our applications. And it shouldn't be that hard. It should be something that we design from the beginning, that we plan for. So let's talk about those abstraction levels. I've said it over and over and over again. Let's just review those abstraction levels as I begin to wind up. We started by admitting, whether it's painful or not, that cancellation is too often thought of as this unexpected exception. And then we said, well, actually you could model it through events, but events have a whole bunch of problems, namely that they can be missed and that they don't compose well. So then we said, well, let's now actually talk about it as a state. That's important and a huge benefit, and if you did nothing else from this talk, moving from event-based cancellation to state-based cancellation would be a huge improvement. But even that's not enough. The final level of abstraction that we need to move to is a collection of states. We need to think about canceling a whole collection of states within our application. So, in summary, if it's async, it's going to get canceled, whether you handle it or not. It's going to happen. And cancellation should not be some kind of unexpected thing. It should be entirely predictable. Unexpected cancellation is what leads to all the uncertainty in our systems. And that uncertainty is what spreads not just complexity, but the unnecessary flavor of complexity. This is a choice that we make through our laziness, through our choice not to think about these things. We shoot ourselves in the foot and create unnecessary complexity. And the final takeaway here is that that complexity is what cancels out all of our software momentum and quality. I want us to be thinking about these things, and I want us to work together to solve them. I don't want a JavaScript solution. I don't want a Python solution. I want a programming solution to handling cancellation as a first-class citizen. I hope I've convinced you as well that that's important. Thanks very much for your time. I appreciate it.